Let's look at the problem. We don't have much time, just 15 minutes for the class. Can't talk about anything else, just directly dive into the problem, okay? This is due today, I think, midnight. And students are asking questions about how to calculate the energy over time. And the reason that you can find the energy without given a finite time point is because this equation is attenuating whatever t, right? Whatever in here. So it's like that. So that's why if you integrate over time, you are able to get a finite answer. So for problem 1, PT is V times I, which is 15 times E minus 250t times 0.04 times E minus 250t as well, and eventually are getting 0.6 E minus 500t. And now integrate it because it's infinite. That's the nature of the function. However, since you know it's gonna getting closer and closer to 0, so you can be comfortable to integrate it over from 0 to infinity, no problem, right? dt, sorry, which is 0, infinity, 0.6 e to the negative 500t dt, which is 0.6 negative 500 e negative 500 t, and the bounds are infinity and 0. And this becomes, with infinity, you plug into this equation. Like I said, negative 500 times infinity will be negative infinity. Whatever, since it's infinity, right? So it could be 0 for this part, and this becomes 1, right? Wait, is that right? No, this is actually yeah. So because it's approaching 0, so this is actually 0, right? Did I calculate it wrong? This is 0, so it's going to be 0 minus plus, this is a minus sign, you change this to plus, so 0.6 over 500, and this is 1, right?
Yeah, plus.
Yeah. So this becomes 1.2 millijoules. All right, it's for the, I think that's first the question. Anyway, so it's asking you, whenever you are reaching half of the energy, what's the time? What's the time point you are reaching half of the energy? You don't have to integrate that again, still keep using this result. I'm not telling you the final answer, but it's very close. So just use 0.6 millijoules, that's the half of the energy, right? Equals, now you want to know T, so you want to keep a T here, right? Still the same equation, 0.6 negative 500 e to the negative 500 t dt. Oh no, keep making the same mistake. I'm sorry. Right? It's already integrated. That's what you got here. So directly use it. Change this bound to t. Okay, so when it starts integrating, at some point, you're getting half of the area below the curve, right?
on the exams, we get a scientific calculator, right? Can we solve this graphically with those?
Yeah.
Okay.
I don't know. I mean, if other sections allows you guys to use it, then we'll use calculators. Is the convention in the past for Calc 1, Calc 2 physics to use calculators or no?
Depends on the course.
Depends on the course. I'll put a note here. I'll let you guys know, okay? Also, there's another question for equation cheat sheet, right? Anything else you wanted me to ask? Other sections? You just have to keep the same for the 300 students. There are 3 sections of 281. Okay? All right, this equation, put the bonds in, calculate t, get the answer. That's for the first problem, and there's another problem in the tutorial that you need to know. I want to clarify. Yeah, so this is still confusing people up, but I know probably 50% of you guys are already very good at this type of problem. So let's just give you another example. For example, this one. Okay, we talked about this a little bit last time. Still want to go through this one more time. Okay, really quick. So, like I said last time, I know we just have to repeat. That's the way to teach, right? You just have to repeat 100 times until the students can get it, which is okay. Let's just repeat it. So when we see a problem like that, what's the first step you want to do? Change it to the real circuit voltages and currents in the real world, right? Real life, right? Whatever it is physically on the board, on the circuit, let's just do it. So for example, is for A, if you see plus minus being labeled that way, being labeled plus minus, and that's the voltage being put in the table. Okay, so plus minus is, so if you use the voltage here minus here, what is funny? No? Okay, cool. So yes, it's negative 25 volts, right? So here minus here is negative 25 volts. So let's just convert it to the real voltage, physical voltage on the circuit. What is that?
Minus plus.
So it's plus, yeah, minus plus from left to right, but right to left it will be plus minus,
Yes.
which is
25.
25 volts. That's a real voltage drop across this guy. Okay. Convert it to the physical voltage first, the real voltage first, and the current labeled is the arrow is pointing to the right, and the current is a positive current in the table. So the current flows that way is a positive current. We just directly write it down. It's 13.75 milliamps. All right. So what's happening in the circuit physically is the current is flowing out from the component. So it's basically delivering power to the outside circuit, right? Why? Because here's the anode. You just always think about like a battery. Here's the anode, here's the cathode. It's always delivering current to the outside circuit. So it's sending power out, right? So it's a negative power first, and it's supplying, delivering, right? So it's not absorbing, it's not dissipating or absorbing, it's supplying and delivering.
So we would know it's absorbing if the arrow of the current was going the other direction.
Yeah, going the other direction, yes. But still have to convert it to the positive number first, to the real circuit, the physical voltage and currents first. Then you can start analyze what's really going on. Let's take another example. For example, B. Take a B. All right. Is it negative voltage or positive voltage? It's a negative voltage again, right? Okay. So physically, for B, it's actually plus minus 25 volts from right to left. And current is a positive current in the table, so we just directly write it down, which is 6.25 milliamps. So in this case, it's actually absorbing because it's flowing current into the anode. If you treat this guy as a battery, so it's actually charging up the battery, even though it doesn't necessarily to be a battery, but just consider this as a battery. So it's flowing current into the anode. So in that case, it's absorbing, dissipating, and it's positive power. All these kind of conclusions you can draw from this. Is that clear for this type of question? And so you get, for this one, you're getting negative or positive power. This. Negative power, right? In terms of this component, it's actually getting the negative power because it's delivering power to the outside circuit. So just put a negative sign in front of it. So for this case, it's a positive power, right? And then you have all the components, negative power and positive power for each component in the circuit, and you add them together, you're getting 0. So that's how you check the balance of the power of the circuit. All right? Is that clear for this type of problem? You'll see this in a lot of places. Okay, clear? Problems. So tutorial 1 is due midnight tonight, right? And homework 1 is Wednesday next week? Monday next week? Okay, so I'm gonna go through some of the difficult problems, not difficult, interesting problems in homework 1 as well today. It's the last time we meet before actually the second last. Monday we'll meet again. But I'll try my best to go through most of the problems in homework 1 as well for you guys. Okay. This one, I think this one is pretty simple. Let's skip it. Let's skip that. Let's just talk about that really quick. So it has a diagram in the problem. It shows you two terminals and labeled as 1 and 2. And it tells you that the voltage from 1 and 2 is negative 2.9 millivolts. So from 1 and 2 is negative 2.9 millivolts. So how do you want to label the plus and minus sign across it for the two terminals? So the description is the voltage drop between terminals 1 and 2. It should be from 1 to 2, right? The drop from 1 to 2. So that's why I think this is a little bit confusing. But however, you should understand what's going on. So the drop between 1 and 2 is actually the drop from 1 to 2. Is negative 2.9 millivolts, I think. Assuming what's the drop. Yeah. So what's really happening here? What's the real voltage drop? 2 to 1, right? Which is 2.9 millivolts. So just ignore that guy. So the description was, the voltage drop between 1 and 2 is negative 2.9 millivolts. So the voltage drop from 2 to 1 will be positive 2.9 volts. And the current entering terminal 1, is 0.9 milliamps, right? Okay, so now you know. It's very similar to the problem we just learned just now. Is it delivering or absorbing? It flows into 1 and then it's going to flow out from 2. Okay, it's going in and then coming out from 2. So if you look at the anode, it's actually delivering current to the outside circuit. So it's delivering and supplying. It will be negative power. So if it asks you, what is the current entering terminal 2? That'll be negative 0.9 milliamps. Okay? Cool. Yeah, I think that's pretty much everything you need to know for tutorial 1. There's another problem for the last problem. Has more numbers. We can come back if we still have time, but I think it's very similar to the one we just have over here. I'm gonna go through homework 1 because it's due Monday, right? That's correct. There's something I want to talk about. If you still have time, we will come back to tutorial 1's last problem. Otherwise, I will just let you guys work on it yourself. Homework 1. So if there's a component, and I think the current, let's just look at the problem, see what's being used here. What's the direction, polarity being used here? I think this is a problem here. Could you see it on the back? Probably not. Let me zoom in. So the voltage and current V and I's are 80 volts. So this is plus minus 80 volts. So from here to here is 80 volts difference. So it's a positive voltage. It's a positive voltage. So we don't have to flip it. It's reflecting the real physical voltage. And current flowing into 1 is negative 2 amps. So the real current is actually flowing that way, right? Which is 2 amps. Because the arrow is pointing to here, but it's a negative current. So that's why the real current is flowing from right to left. Okay, so now we have the real voltage and real current for the component. So we can do a lot of calculations. So I think one of the questions is asking you if the electrons is gaining or losing power or energy by moving into terminal 1. How do we look at it, look into that? So if current flows that way, we know electrons flowing the other way, right? We learned that in physics, right? So the direction of the current is the opposite direction of the electron flow. It's just defined by electrical engineers. So what's really happening in the circuit is you have a battery, you have a resistor to close a loop, you get a circuit like that, right? So because here has a higher potential, here's just 0 volts. So it's gonna push current that way, and we label that current as I. If it's 5 volts, this is 1 ohms. So we're getting 5 volts over 1 ohms, which is 5 amps. So that's the amount of current, and this is the direction of the current. It's going back to the cathode of the battery. So what's really happening in the circuit is current is just a definition, but what's physically really happening, usually we don't think about that way. We just ignore the electrons. We want to care about currents. So physically happening in the circuit, in the wire, is the electrons are moving backwards. That's how we define it. Don't need to dig too deep into that. Just need to know. Usually we just use currents, so it's in the opposite direction of the electron flow. Okay, so for this case, because current flows that way, so electron flows that way, right? Okay, so if you draw an electric field, because here's positive, here's negative. If you have an electric field, and think about this plus and minus is forming electric field inside, like that, in that direction. Okay. So because electrons are moving from negative to positive, right? So electrons are moving that way inside the terminal, inside the component. So it's actually losing power. It's actually losing power. Why? Because the force of the electrons, if you have a source charge and a testing charge with the electron, the force equals KQ. I couldn't remember it, but it's a function of distance. So distance is at the denominator. So if you get a larger distance, you are getting less force. So it's moving towards here is losing power, losing energy. If you move electrons from negative to plus in the electric field, this is it just understand what's going on here, but we rarely do this in dealing electrical circuits. Yeah, it's just physics stuff. Some of the problems I really don't like. It's okay. Just need to know. If you see the problem, now it's it's losing energy. Okay. Here another problem. I don't have a problem number on the printed view, but if you look at this equation, you should be able to know which problem that is. It has V equals T3 minus T from 0 to 3 seconds. And I, which is current, equals 6 minus 4t. This is a milliamp. This is volts, okay? And from t from 0 to 3 seconds as well. So the questions are, at what instant of time is power being delivered to the circuit element maximum? So power is VI, right? And because both of them are functions of t, it's 3t minus t squared times 6 minus 4t. That's milliwatts. Which is 18t minus 12t squared minus 6t squared plus 4t to the third power, and that's milliwatts. And which is 18t minus 18t squared plus 4t third power. What's next? So to find the maximum, do a derivative of the p over t. So dp t dt becomes 18 minus. So see, this is how you spend a lot of time on algebra instead of electrical circuits. 36t plus 12t squared, and you make this to be 0. And you can simplify this one, divided by 6, I think. So it becomes 6t, 2t squared minus 6t plus 3 equals 0. So t equals right? Minus b, minus 6, plus minus. Is that correct?
Yeah, that's what I thought. The 6 should be positive.
6 would be positive.
Because it's negative b.
Oh, that's right. 6 plus minus what? 6, 20, 24, right? 12. Is there a solution here so I can directly use? Do I have it? Okay. So this is 3 plus minus square root of 3 over 2. Now you are getting T1 is 0.634. Are we getting milliseconds or seconds? Because power is millipower now, milliwatts. I think that's milliseconds, right? Let's use milliseconds for now. But the solution is seconds.
Yeah, I don't think T is in.
What you think? T
T has been seconds. This time.
oh T has been seconds, yes, over here. Yeah, T has been seconds. Yeah. So this is this much. T2 is 2.366 seconds, like that. And so you can calculate. There's something can be confused. That's why I want to write it down. Otherwise, I wouldn't do this. And you can plug in the T's to the equation, and you're getting milliwatts, right?
Yes.
So this becomes 5.196 milliwatts, and PT2 becomes negative 5.196 milliwatts. At these 2 time points, you're getting these 2 power. So which one is the power being delivered? Which one is being, if you look at the question here, the question here. So this problem tests your English and your physics and your Calc 1, and not Calc 1 even, and algebra, but not circuits. Just kidding. At what instant of time is the power being delivered to the circuit? Delivered to the circuit, what does that mean?
Power being absorbed.
Yeah, being absorbed by this component. So which power you want to use for from the calculation? The positive power. Just going back and forth all the time. So when we are talking about the component can deliver power to the outside circuit, right? But now we calculate everything for that component or that circuit. Okay? Something delivered to that circuit is that circuit absorbs. Alright? And these voltage and currents are the voltage and currents being measured, that voltage and currents for that component or for that circuit. So it's basically something getting into it, flowing into it. Which doesn't make, a perfect sense, but we can understand it that way, and we can get the correct answer, and that's it. Don't get struggle and don't hate electrical engineering from now on. It's just some English stuff in the problem description. As long as, so let's say that, if we use the master engineering problems, you guys get the experience of calculating all the voltage and currents and power and the circuits and all this kind of stuff. So the outcome, by the end of the semester, you understand voltage, you understand KVL, KCL, whatever superposition, all the electric engineering stuff, basic fundamentals of circuit 1 stuff. That's the outcome. That's the final outcome. That's what we want to achieve at the end of the semester.
With this problem, what were the bound between 0 and 3 used for? At the very beginning, it says we're bound between time is bound between 0 and 3 seconds.
Yeah, but we are not integrating it, are we? Let me see. The first question is delivered, the power delivered. Oh yeah, so we have to. No, it's just the maximum, right? Just 1 point. It's not an overall.
There's another question.
There's another question. Okay.
Oh, there's another question.
What is the power at the time found in the previous? What's the power? Okay, still a component. And at what time is it being extracted? Okay, so there's a part D, right? Part D is what's the power at the time from the. It's also time. It's also a time point power calculation. So the last one.
They use it for part E.
Yeah, part E, right?
Yeah.
Okay. Calculate the net energy delivered to the circuit at these time points. So I got a bit confused at the very beginning, but eventually I find out it's net energy, which is the overall energy being delivered to the circuit overall. So you just have one integration, okay? And you'll find the function of energy in terms of time. Then you plug in the time points into it. So now let's write it down for you guys. Okay, part E, right? Part E. This is 4. Okay. It's just a 0 to 3 seconds for a question. And the equation was the original equation without getting the derivative, which is this part, right? So this is the power, and you integrate that power from 0 to 3 seconds. 18t minus 18t squared plus 4 times t dt, and you found that eventually, and you just calculate E0, E1, E2, and E3, right? So these should be all the answers for the question. Okay? Any other questions?
To evaluate that way, wouldn't you want to do an indefinite integral to get a general expression for E, unless you're going to change the bounds every time you do the integral?
That works too, I think. But I think if you get a function of the E in terms of t and plug in the numbers will also work, right?
Yeah.
Either way. There's another question, another problem here. May need your attention. This guy, okay? This guy. You know this is recorded, right? Make sure you watch the video if you still have questions. This is another algebra problem. So first one is asking you about the charges. So charges is integral of I t dt. If it asks you about the charges, it's basically just area below this curve, right? The current time, integrate from 0 to 20 seconds, and find out that charge is easy to calculate. Just find out the area of the triangles. We'll do the trick as well. Triangles and rectangle, 2 triangles, 1 rectangle, just find the area. And for the second problem, it's asking you for the power. As for the power, we know power is V times I. We know power is V times I. But since they have different linear equations, so that's why you have to find the linear equation here first. So have different sections of time. It's going to be from 0 to 15 kiloseconds. So the linear equation for this curve doesn't change after 15 seconds. So when t from 15 to 20, you have to change the current's linear equation. You have to use this one times the same linear equation, and then you integrate with different bounds for these 2 sections. Okay, these 2. And anything after 20 seconds, you still have voltage, but there's no current, so the power is 0. So you just ignore anything about anything after 20 seconds. So all the calculation stops at 20 seconds because the current is 0, even though it still have voltage. It's not delivering any power. Okay? Any question about this problem? Fine? Works? That's homework 1. Let's come back to the problem in tutorial 1. So many voltages and currents. Should we do it? Let's probably do several of them. Some of them. So look at the labels. The label here is what is this one asking you? I think 9.5 volts plus minus 9.5 volts. Sorry, V2 equals 9.5 volts, and currents I2 is 2.5 amps. V4 here is negative 4.9 volts. Okay, let's calculate. I don't want to write everything down, it's just too many of them to save some time. So let's just look at this one, for example. So we are doing the power balancing calculation for P2. How do you want to put in there? What you want to put in there? So this is positive 9.5 volts. And you are getting a positive current, so we don't have to change anything. This is the real voltage and real current physically in the circuit, right? Is the current flowing outside of the anode or inside the anode? It's going out, right? So it's going to be a negative power. It's 9.5 volts times 2.5 amps. Number 4. There's I4 here, which is 1.6 amps. Because it's plus minus, but the voltage is negative, so I have to flip it, right? So the voltage is actually the real voltage across the component is actually this, about 4.9 volts. And now I'm getting the current flowing into the anode. It's charging up the battery, if it's a battery. So P4 is positive 4.9 volts times 1.6 amps. Okay, just keep doing this for all the components. You can get and add them together. It should be 0. Okay, if it's 0, you check the balance, power balancing, the power balance the power. Otherwise, check no. So it's asking you yes or no. Any questions about this? Another question about tutorials. I think the other professor who has taught this one for many times, he's managing the mastering engineering problems, and he said all the tutorials will be extra credits. So if you do it, you are getting your grade boosted definitely. So even though it's labeled as 0 points in Canvas, but you are highly encouraged to do it. I think, but how many points, right? Sometimes you're thinking bonus points, but how many? That's what we do the math, right? Or what we do the business. So I was looking at the numbers he posted at the very beginning of the semester. I think for the entire homework assignments for 11 or 10 assignments, it's totally about 360 something points. And the tutorials are 40 something points. I think it's not super significant, but it's something, right? It's about 10%. So please work on it if you have the time to do it. And there must be some bugs or little issues, but minor, I think, since I've used the same problem set for the previous students. So if there are some bugs in the homework assignments, you are losing point, and you shouldn't actually, because you know the answer, it's just not matching the perfect answer sometimes. But since you have the tutorials, it's probably compensating you back a little bit. You're getting more points, so I think it's relatively fair. But you are investing time into it anyway. There's no perfect solution to it if we have like 100 students in a section. Just trying to do the best we can. Tutorial 2. It's already posted, right? You can start working on it if you want. KCL. Kirchhoff's current law, and which is all the currents flowing into the node, the summation of all the currents flowing into the node is 0. So basically this is I1 plus I2 plus I3 is 0. The reason this is true is because I1 plus I2 equals minus I3. If you look at the node, it could be any node in the circuit, if you have a circuit here. Okay? Here's a node, right? So the current flowing into it, if you add them together, it's going to be 0. The reason for that is, if you flip one of the current, and this becomes the summation of the current flowing into the node, equals the current flows out from the node, because you flip it, right? So if you do the calculation in the way that they all flow into the node, and you are using positive currents, you add them together like I1, I2, I3 flowing into the node. Okay? Then the summation 0 is because if you move I3 to the other side of the equation, it becomes a negative current. If you look at this same diagram here, so I3 flowing in, which is the same as I3 flowing, negative I3 flowing out, right? And we know this is true because all the currents flowing into something equals the current flowing out from that same node. It's not losing currents. It shouldn't go to anywhere else. Just a one node, just one metal piece. So everything flowing in terms of current, all the currents flowing into some node in the circuit equals all the current flowing out from the node. Is that making things easier to understand? So always imagine that the current's flow is very similar to water flow, right? You have multiple tubes or pipes connecting to one node, and for plumbing purposes, right? So several pipes or 2 pipes. Let's just make it easier for now. Okay, the water flow going into one node does not equal the water flow coming out from the node. Is that possible? No, it's going to be the same current flow. So the 2 current flow or water flow coming into the junction equals the merged water flow going out from the junction. It's the same concept. However, if you flip this current to the other direction, you are getting a minus current. right? So in that case, you add them together, so all the current flowing into the node becomes 0. That's KCL. We use this a lot in the semester to calculate currents. So for example, the question here is, a circuit node. What is a circuit node? It's just certain metal piece in the circuit. Node. A certain node, a certain metal piece in the circuit. Could be here, could be here, could be here, 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 anywhere in the circuit. Okay? So the question is, a circuit node, a node has current IA entering, and so IA is entering, IB and IC are exiting. If IA is 5 milliamps, IB is 9 milliamps, what is IC? What is IC? Yeah, that'll be 5 minus 9 milliamps, which is negative 4 milliamps. Okay? So the actual current is actually flowing into the node because it's getting a negative current flowing out, so it's actually flowing in physically. However, you can always use vectors for the calculation and using KCL to calculate it without any problems. But eventually you get an answer, it's going to carry a sign in front of it. So you'll know the real current direction in the real circuit. Any question about KCL? It is just that simple. Okay? You could do either, so when you are doing circuit analysis, you could do either find find all the currents flowing into a node and add them together equals 0 to calculate some variables in there, or you can just find out all the currents flowing into it and put it on the left-hand side of the equation, and find out all the current flowing out from the node and put on the right-hand side of the equation, and they equal to each other to calculate variables. Either way is gonna work, okay? Depends on your preference calculations. Let's see an example here. Oh, I don't have more examples for KCL, but in the future we have to do KCLs. Now introduce KVL really quick. KVL. There are just two main voltage and current laws. KVL, which is Kirchhoff voltage law here. It's if I draw a circuit like this, I label it as plus minus, minus plus, plus minus. This is V1, V2, V3. So when you are doing KVL, it's actually very useful, super useful. In the future, you'll use it a lot. When you do KVL, you start from a point, anywhere in the circuit, just start from there. I usually start from the bottom left bottom corner. So I'll draw a little guy here, traveling clockwise through the circuit, okay, and come back to the same point. So what do you want to do for KVL? So list all the voltages for every single component. If this guy see a plus first, keep a plus sign in front of the voltage. If this guy see a negative sign first, keep that negative sign in front of that voltage. And put them together on the left-hand side of the equation, and that equals 0. That's KVL. Instead of put a long paragraph here, I'll just give you an example so you'll know how to do it in the future. So now let's go through it, okay? For a very simple KVL problem. So what's the equation for all the voltages? When this guy starts traveling, right? equals, that's it. So if these two voltages are given, it's asking you to calculate V3, and you can do it. Any questions for this? Could the voltages, could V1 be negative?
Could be.
Yeah, it's vectors, right? Could V2 be positive or negative? Doesn't matter. There's nothing to do with the labels. They can label whatever they want. And the voltages can be negative or positive. Doesn't matter. We just plug in to the equation and equals 0 to calculate any variables in the equation. Okay? Alright, we'll see you guys on Monday.